In this video, I'm explaining homework number 2, the written part. Question 210C, we have an egg that is cooking in a boiling water. So we assume it's a round spherical shape, and we model that as a one-dimensional with a symmetry, and it's a transient heat transfer process. Question 224, there is a cylinder and we want to start with an energy balance to find out the one-dimensional heat conduction equation for it. So we assume it's one-dimensional, steady state, and constant K with internal heat generation. And we start with energy equation and cancel out the terms and take a limits, and we get the final heat equation, the conduction equation. Question 266, there's a flat plate of solar that there's some tubes of water on the back of that, and we need to find the temperature expression in the x direction. So we use the energy balance for it, and we use the boundary condition as well, and we find the Tx. And after that, we need to find the Q that absorbed by the solar collector too, that we can stop in the numbers that we have and do that as well. The next question is question 2102, that there is a long homogeneous resistant wire that we need to write the radial R direction is a steady state again and one-dimensional. So we start with the radial equation and keep that going. I use the boundary condition, integrate twice, and find the temperature profile on it, and after that plug in the numbers to get the temperature when R is equal to 0. Question 1429. So we can consider the on the free surface of the lake that if it's saturated, the fraction of the water vapor, the mole fraction of water vapor in air is the same as the lake, because concentration is not a continuous function. Question 1435C. So the mole fraction of vapor is P saturated vapor at a temperature divided by the P total, the P atmosphere. And question 1440, the last question, it asks us to find out the mole fraction of vapor, that we use the formula that we used on 1435. And after that, it needs to find out the mole fraction of dry air in the liquid side. So we find the Henry's constant from table 14-6, and we calculate the P dry air by P minus P vapor, and we divide that by the Henry's constant and get that Y dry air.